its like cost, right? Yeah. Yes, Thieshanthan, I think you can start.
I'm trying to share my screen. Is it up already?
Yes, Thieshanthan, we can see your screen.
Yeah, thank you. So this is a paper about self-supervised learning from 2022, I guess, early 2022. So here they propose a simple training scheme to kind of train self-supervised architectures. So can check that. So before starting, can look into the basics of like what the self-supervised learning is about. So in a typical setting, we have our data.
Do you want to move the like presenter mode or?
Yes, yeah, I forgot that. Sorry.
Right.
Yes. So we have our data distribution and we sample two sets of images, like say we get X and X dash, which is like similar, but we apply different augmentations. So like color croppings and different color schemes. So they look different, but we want to like recognize the same features in both of them. And then we typically use two embedding networks to get to different embeddings. And then to kind of get these embeddings into a same space, so we can kind of compare them. We have this two extra network which can project them into the common space, where we can kind of match the similar features and kind of push away the not similar features. So this is the typical setup in the self-supervised learning. So the problem generally arises there is like when we kind of start to train the network, the embedding network tends to kind of not produce these embeddings in a good manner. Like they will like every different augmentation will kind of produce the same embedding. So there will not be much to learn. So in this paper, they are proposing a simple method to kind of stop that collapse problem, where these embeddings fall into same plane and kind of have less meaning. So this architecture becomes very less usable. So they propose like kind of three loss terms. So basically what they're proposing is an
So the paper, can you go to the first slide? Yeah, so when was this paper published? It's a recent paper or?
Yeah, this was around, the last version is 2022 January.
Okay, I see. Yeah.
Yeah, so
yeah, I think.
So they are proposing three loss terms. So the idea is to like kind of have the invariance and the variance and the covariance, and this comes as the name, and this reg stands for the regularization. And they are proposing is they need to like bring the similar features closer. So they have this invariance term, and the variance term is like basically to kind of keep the variance between the samples in the batch. And they propose a new term, covariance, which is like applied to a single embedding. So the single embedding in all the dimension, each dimension has a different set of feature. So if you have a feature vector, it has 248 something vector. So each of those place like kind of embeds a different detail. So that's the purpose of this covariance term. So if we kind of look in the architecture, so here we have different number of batch samples in the batch. So the variance term kind of increases the variance between this batch, so everything doesn't fall into one thing and doesn't collapse. And the covariance term ensures that each place of this feature vector kind of have a different information from this encoder. So we kind of maximize the information gained from this network at improving the performance wherever we are going to use this. And basically the invariance term is like kind of bringing these two features closer or kind of pushing this far away depending on what we are here we are selecting. So if we select two similar features, similar images, this thing will be like brought closer. If these things are not similar, this will be like this doesn't want to come closer. So that's the basic idea.
Can you go
So
back to the diagram?
yeah.
So yeah, can you briefly explain the problem? I think I was a little distracted when you said that part.
Okay. So you're okay with the architecture, right? Like we have two different branches to kind of have two different embeddings.
Why do we have Y here?
Yeah, so this is our network. This is the embedder. So how we are going to use this is like we are going to learn the features from this data distribution. So what we are going to do is we are going to feed two views of same sample. So they kind of give different features, but we know they are from the same sample. So we kind of need to bring that closer. So this network kind of learns to get the samples, like get the features of the same samples.
So it's basically contrastive learning, right?
Yeah, contrastive learning. Yeah. So
and why do we have H?
Yeah, so these two features doesn't need to be on the same space. So this can be anywhere, but we cannot use our loss functions directly to them. So we have these networks called the projection networks. So this will like kind of bring this into a single vector or something. So this can be like any amount of features. Since this is typically a convolutional network, this will be like a 2D vector or whatever the dimension is. So here we'll have like a smaller thing, which is like kind of projected.
Okay. And Y and Y dash, are they similar dimensionality?
Yeah.
Okay. And
So typically, yes, but here they kind of say in the end that it is not required, since these guys doesn't assume that.
Okay. And the architecture, if theta and if dash theta dash and H5 and H dash theta Y dash, they are also are the same architecture, or?
Yes, typically before this works, they kind of use the same network, like same architecture with like same weights. So this would be like just F theta, and here also F theta. But here, since these assumptions doesn't require anything to be same, so they are using different networks.
I see. So this is like a more general form, but like what they demonstrate in the paper is like a somewhat simplified version of the more general form.
Yes, they claim it, but almost all of the experiments like uses the same thing.
And the weights are also same, F theta and F theta dash weights.
Yeah.
Okay, so it's the same encoder and then like the same projection.
Yeah.
Okay.
Yeah. So what happens if we just use this is like after some time this Y and Y dash are like have no like kind of difference. So they tend to go to the same area. They call it the collapse. So to avoid that problem is what these guys are proposing, these loss terms.
Okay. But when they're training it, like they are also training with different examples, like not only the so in this, according to this diagram, what I see is like you get the same examples and you augment one and then try to minimize the distance, right?
Yes. So
and
I think I said it wrong. So generally, like in sim class sort of things, like they get everything and the loss automatically works. But here it should be the same sample, I guess. Because it's just a Euclidean function, they are just using it to bring it closer. Yes. So moving on. Um, so this is the first term, basically the variance. Here they use a hinge loss to kind of promote the variance among the batch, so among the samples. So this kind of ensures like nothing in the batch goes to the same place. So what they are trying is to have the variance among the batch to this gamma. So it always like has a gamma of something. So everything is like kind of different. So information is preserved. So this is the basic term they are introducing to avoid the collapse. And we have the invariance, which is basically like bringing closer those two features. This is just the Euclidean function between like every pair. So everything is similar. So we need everything brought closer. And they have another term, covariance. So this is just a covariance matrix, but what they are trying to achieve here is like bring the covariance to like 0. So within the dimensions of a single vector. So what that ensures is like none of the dimension has the same information. It avoids the collapse as well. So they just have these losses added together. So it's just some hyperparameters here, and they just add all these loss functions. So they just optimize with this loss function. So it basically simple with all the terms are basically simple, unlike Sinclair or anything like where we need like contrastive samples. Here we don't need them. We just need simple augmentations to just create the net, like the training process. And also it doesn't require, like it doesn't assume anything on these batch sizes, like they should be large as Sinclair or something to ensure the variance, like which their loss function automatically does for them. But here they don't assume anything. And also the gradient is like just follows through, unlike other networks which has some conditions for this and this, which like kind of forces them to have the same thing. Here they don't need to have that. And I think I said that as well. Yeah. And so their claim is like the information is kind of uh, preserved here and without doing a lot of data and without kind of having a very large batch size and having to iterate over the gradients after collecting a lot of features. So this tends to be a simpler method to use uh, self-supervised learning. And if we check out the results, so these guys used it on the ImageNet. So to use this network, what they basically do is like they train it and they kind of discard this projector networks and kind of have another layer of thing to kind of do the task. So here for ImageNet classification, they kind of use this feature extractor and have another linear classifier or something else to kind of predict the classes. So they have two kind of networks, which is just a linear classifier and a simple network using semi-supervised ideas. Like they kind of use some data to train that as well. So to check this performance, they like very close to state of that and like very high from Sinclair. Um, and also they kind of have somewhat better performance in the semi-supervised areas. Also, this network kind of performs well in the downstream tasks, so where they can use the feature extractor to kind of achieve other tasks like object detection and classification. So in other data sets, there also they kind of have some good accuracies. And yes, yeah, to conclude things, so this doesn't have any like complex requirements from the network architecture. So as there was no assumptions made, it's just improving the variance and covariance between the data and embeddings. It doesn't need everything to be on the same plane, same space. So this gives freedom to kind of select different methods for each branch of the network. And what they optimize is what they call the triple objective to promote invariance. So that's basically like bringing closer the samples and preventing collapse within a batch by keeping the variance among that batch, that feature batch, to a constant value, and kind of using the covariance to ensure that each embedding of the vector kind of has a different information. So they have very rich set of information. And as I was saying, this does not assume anything on the architecture. So both branches are allowed to be different and they can be anything. Yeah.
So I guess like one question is, during training, are they showing like one set of let's take one batch, and for that batch they are showing that batch to f theta, and then for the other branch they are showing an augmented version of that,
Yes.
right? And there's no other like combinations. For an example, they show one batch and then a different batch and then try to increase the distance between the two.
No, here they are just reducing the distance. So that's why they claim it to be simple.
Okay. But in some sense, are they in these loss terms, do they also somehow kind of like use the information that within the batch some images are different?
Yes, that's why this variance term is for like, so this ensure like two same images doesn't fall into the same thing.
So if does that mean like the arrangement of the batch, like how you select the batch, affect the performance? For an example, if we have images from the same class in one batch, they are more similar, right? Whereas,
Yes, I'm not sure about that. Yeah.
in other words, like, do they have to really like randomize the training data set?
Yes, in their claims, like it's completely random. The other methods, but if we are going to push this away, we need like contrastive thing to build up here. So what they are doing is kind of pulling things random. So which like eases a step because we don't need to know the classes first. So this can be like truly unlabeled.
Mm-hmm. But in other words, like, have they done any test with like different without randomization?
I think it was not clear in their analysis.
To me,
They
it sounds like
tried.
how they select the mini batch will affect things a lot.
Yeah, it wasn't there in the paper, I guess.
It's anything on the size of the mini batch, like.
Oh, yes, that was there.
So for an example, if the mini batch size is 1, this shouldn't work, right?
So the batch size is like 2048. Yeah, it's a very large batch size. So they have fixed it for everything. Sure.
Might be some ablation or supplement or something about the batch size.
Yeah, the batch size is like kind of fixed to this value. And they provide in the analysis section is like kind of using different architectures and different architectures and like sharing the weights between the same architecture. So that's highlighted in the analysis, not about the batch size.
Thieshanthan, I think in D7 section, if you can quickly go, table 13 specific.
Sorry, the 7 section.
Table 13. I think it's on table 13.
Yeah, it's there.
Yeah, so the batch size according to this results doesn't matter too much.
Yeah, I guess.
Is there anything referring table 13? Like the text batch size, yeah.
Yeah, it's there.
I see.
Thieshanthan, I have a quick question. So usually when training on GPUs, like what's the batch size we can usually like if we take ImageNet, for example, like what's the maximum batch size we can go on a single GPU based on your experience?
Yeah, so the ImageNet is like basically 2 to 4 in like width. So like if we use a 16 GB card like Tesla T4 or something, cannot go far beyond like 32 if we have a larger model. So it like requires a cluster to like anywhere between these ranges.
Right.
Interesting. So this paper is 20 something, 20, did you say 2022 or?
Yes, so it
Yes,
was like, yeah, they first gave it on like May 21 and the last version is around January 22. This is on ICLR 2022.
I see. Yeah. All right, sounds good. Any other questions?